Chapter 1: The Century-Long Mistake. For almost 100 years, the global scientific community lived convinced of an astronomical falsehood. It wasn't a deliberate deception or a conspiracy, it was something far more human, an error born from technological limitations and perpetuated by generations of brilliant astronomers who simply couldn't see beyond what their instruments allowed. The story begins with that faint smudge in the heavens that has fascinated humanity since time immemorial. Ancient Persians, observing the sky with their naked eyes, poetically dubbed it the little fish. European astronomers in the Middle Ages, equipped with the rudimentary telescopes of their time, classified it as just another nebula, never imagining the sheer magnitude of what they were observing. It was merely a footnote in celestial catalogs, a diffuse object among thousands. But everything changed in 1923. That date marks one of the most revolutionary moments in the history of astronomy, yet also the birth of the most colossal error that would take us nearly a century to correct. If these fascinating revelations about the mysteries of the cosmos help you relax and disconnect from your day, I invite you to subscribe to Deep Space Calm. Our channel is specifically designed to accompany your moments of rest. Every day, we explore new astronomical wonders with tranquil narrations that transport you to the universe as you prepare for sleep. Join our community of stellar dreamers. Edwin Hubble, yes, the same man the most famous space telescope in history is named after, pointed the Hooker telescope at Mount Wilson Observatory toward Messier 31. This instrument, with its 100-inch mirror, was at that time the most powerful ever built by humankind. And what Hubble discovered that night so radically transformed our understanding of the universe that we are still assimilating the consequences. Messier 31 was not a gas cloud within our galaxy. It was another complete galaxy. An island universe, separated, just as the philosopher Immanuel Kant had speculated almost 2 centuries before. Suddenly, the universe became immeasurably larger. We were not the only galaxy. We were one among countless others, floating in the immensity of space. It was a discovery worthy of the Nobel Prize, but it came with a problem. Hubble and his contemporaries needed to determine just how big this neighboring galaxy, which we now called Andromeda, truly was. This is where the error began. The astronomers of the 1920s and 30s did the best they could with the available tools. They measured the brightest stars they could detect. They analyzed the light captured on photographic plates. They applied the most advanced mathematics of their time, and they reached a conclusion that seemed irrefutable. Andromeda was a giant, maybe twice as massive as our Milky Way, possibly 3 times. The narrative was seductive. We had discovered our cosmic big sister, a galaxy that eclipsed us in size and gravitational power. In the distant future, when these 2 galaxies finally collided, because yes, even then we knew we were on a collision course, it would be a conquest. Andromeda, the giant, would absorb the modest Milky Way. This idea became deeply ingrained. Textbooks taught it as established fact. Academic lectures cited it without question. Computational models of the future galactic collision assumed it as a basic premise. For decades, generation after generation of astronomy students learned that Andromeda was the dominant force in the local group of galaxies. There was only one small problem with this compelling narrative. It was fundamentally wrong. But how did this error happen? How did brilliant scientists, using the best instruments of their era and applying rigorous scientific method, arrive at a conclusion so far from reality? The answer teaches us a crucial lesson about the nature of science. We can only discover what our instruments allow us to see. And in the 20th century, Even with the most advanced telescopes of the time, vast regions of Andromeda remained completely invisible. Imagine trying to measure the ocean by looking only at the waves on the surface, or calculating the size of an iceberg by observing only the small tip emerging from the water. This is what studying Andromeda was like with early 20th century technology. Terrestrial telescopes, no matter how powerful, had to look through miles of turbulent atmosphere. The light from distant stars was distorted and twinkled as it passed through this moving mantle of air. Faint stars, especially those in the outer regions of Andromeda, simply got lost in the noise. The photographic plates of the time, while representing cutting-edge technology, had limited sensitivity. They could capture the bright regions of the galactic core and the most luminous spiral arms, but the faint areas of the outer halo remained invisible, as if they didn't exist. And here is the critical problem. The majority of a galaxy's mass is not in the bright regions. It is in the halo, that vast spherical region surrounding the visible disk, populated by ancient, faint stars, and enveloped in invisible dark matter. And this region was completely undetectable to 20th century astronomers. So, what were they actually measuring? Only the bright core and the luminous spiral arms. It was as if an alien tried to measure the size of the Earth by observing only the illuminated cities at night and ignoring all the dark oceans, forests, and deserts in between. But there was another dimension to the problem that would make this error even more persistent: scientific confirmation bias. Once the idea of Andromeda the Giant was established in the literature, every new observation was interpreted through that lens. Data that didn't fit were dismissed as measurement errors. Theoretical models were adjusted to accommodate the premise that Andromeda was significantly more massive than the Milky Way. It wasn't malice or incompetence. It was simply how science works when operating under severe technological limitations. Scientists build models based on the best available data, and then those models become so ingrained that overwhelming evidence is required to overthrow them. And so, decade after decade, the error persisted. The 30s became the 40s. The 40s became the 50s. Telescopes gradually improved, observation techniques were refined, theories became more sophisticated. But the fundamental belief about the size of Andromeda remained unquestioned. Even when the 60s and 70s arrived, with significantly more advanced telescopes, the paradigm held. Astronomers were looking deeper into space than ever before, discovering quasars, detecting cosmic background radiation, revolutionizing our understanding of the universe. But about Andromeda, our closest neighbor, we were still wrong. Almost 70 years had to pass since Hubble's discovery before the first cracks in this seemingly solid paradigm began to appear. It wasn't a single dramatic discovery, but a gradual accumulation of contradictory evidence, small anomalies that didn't quite fit the established model. Andromeda's rotation curve, the way stars orbit the galactic center, didn't exactly match what would be expected of a galaxy with the assumed mass. Satellite galaxies orbiting Andromeda moved in ways that suggested a slightly lower gravitational pull than predicted. Computer simulations of the future collision produced strange results when traditional mass values were used. They were small discrepancies, easy to ignore individually, attributable to measurement errors or simplifications in the models. But collectively, they began to tell a different story. Then came 1990, and with it, an absolute game-changer: the launch of the Hubble Space Telescope. Hubble was different from any telescope that had existed before. It wasn't on the ground, looking through miles of distorting atmosphere. It orbited above all that, in the vacuum of space, where it could observe the universe with unprecedented clarity. Its detectors were exponentially more sensitive than the old photographic plates, and it could point at a target and maintain that position with perfect stability, for hours or days, accumulating light from objects so faint that no terrestrial telescope could ever detect them. But here's the fascinating thing. Even with Hubble in orbit, the error about Andromeda wasn't corrected immediately. Science doesn't work that way. Established paradigms are resistant, and rightly so. We don't want to discard decades of scientific work for every new observation that doesn't perfectly fit. It took years of careful observations, meticulous analysis, and rigorous scientific debates before the astronomical community finally accepted the unthinkable. We had been mismeasuring Andromeda for nearly a century. The correction didn't come from a single study, but from multiple lines of converging evidence. Astronomers began to measure the motion of individual stars in Andromeda's halo, something impossible before Hubble. They studied the dynamics of satellite galaxies with unprecedented precision. They tracked stellar streams, the remnants of small galaxies torn apart by Andromeda's tidal forces, to map its gravitational field. And all these independent measurements converged on the same shocking conclusion. Andromeda was not 2 or 3 times more massive than the Milky Way. It was approximately equal in mass. The two galaxies were cosmic twins. The definitive announcement came in 2012, when an international team of astronomers published the most precise measurements to date. They had used years of accumulated Hubble data combined with observations from advanced ground-based telescopes. They had applied sophisticated analytical techniques impossible in previous decades, and their conclusion was unequivocal. The error had been a factor of 2 to 3. For almost a century, we had overestimated Andromeda's mass by 200 to 300%. It was an extraordinary moment in the history of astronomy, not because it revealed something unexpected about the universe — galaxies the size of Andromeda are common — but because it demonstrated how profoundly wrong we could be, even about objects we had studied for almost a century. And it revealed something even more beautiful, that science, despite all its temporary errors, eventually corrects itself. New technologies allow new observations. New observations generate new questions, and eventually, no matter how long it takes, the truth emerges. Andromeda was not our future conqueror. It was our twin. And that realization completely transformed our understanding of what would happen when these two galaxies finally collide in the distant future. It wouldn't be an absorption. It would be a merger between equals, a cosmic dance of truly comparable titans. But before exploring that dramatic future, we need to understand exactly how this error developed and why it took so long to correct. Because this story is not just about Andromeda. It's about the very nature of scientific knowledge and human limitations in the face of the immensity of the cosmos. Let's return to 1923, to the moment of Hubble's discovery. Historical context matters here. World War I had just ended. Einstein had published his theory of general relativity just 8 years earlier. Quantum mechanics was in its early stages of development. Astronomy as a modern scientific discipline was just finding its feet. When Hubble identified Cepheid variables in Andromeda, pulsating stars whose variable brightness allows for the calculation of astronomical distances with precision, he didn't just discover that Andromeda was another galaxy. He also calculated its distance, approximately 900,000 light-years. His number would also turn out to be incorrect. The actual distance is about 2.5 million light-years, but that's another error for another story. With the distance established, the next logical step was to determine the size, and this is where technological limitations became crucial. Astronomers could see the bright center of Andromeda with reasonable clarity. They could distinguish the most prominent spiral arms, but the outer regions, where the density of stars gradually decreases, faded into the darkness of the background sky. Imagine looking at a city from a nighttime plane. The densely lit areas of the center are obvious. You can see where the tall buildings and main streets are. But where exactly does the city end? In the scattered suburbs that barely shine? At the isolated houses on the periphery? The boundary is diffuse, arbitrary. This is what measuring Andromeda was like in the 1920s. Astronomers of the time made a reasonable decision. They defined Andromeda's size based on where they could detect significant light emission, and based on that, they calculated its mass. But unknowingly, they were measuring only a fraction of the actual galaxy. As the decades passed, telescopes gradually improved. Mirrors became larger, photographic plates more sensitive. Astronomers could see a little further into Andromeda's outer regions. But each improvement was incremental, and each new measurement seemed to confirm the basic estimate. Andromeda was big. Very big. Significantly more massive than the Milky Way. What no one realized was that even with improved telescopes, they were still only measuring the brightest parts. Andromeda's true halo, the ancient, faint stars stretching for hundreds of thousands of light-years, remained invisible. And there was another complication: the Milky Way. To compare Andromeda with our own galaxy, we first needed to know how big the Milky Way was. But we are inside it, which makes measuring its true size extraordinarily difficult. It's like trying to measure the size of a forest when you are standing in the middle of it, surrounded by trees in all directions. So, the estimates for both galaxies had significant uncertainties. And when you combined those uncertainties with the limitations of the Andromeda observations, the composite error magnified. The 1950s and 60s brought significant advances in astronomy. Radio astronomy emerged as a powerful tool. Scientists discovered that Andromeda emitted detectable radio waves, and these radio observations could penetrate the dust that blocked visible light. For the first time, astronomers could see parts of Andromeda that were invisible in optical light. But even these revolutionary observations didn't completely correct the mass error. Why? Because a galaxy's mass is not just in its visible stars or detectable gas. Most of it is in something completely invisible: dark matter. In the 1970s, astronomer Vera Rubin made revolutionary observations of the rotation curves of galaxies. She discovered that stars in the outer regions of galaxies moved much faster than they should according to the visible mass. The only explanation was that there was additional, invisible mass, dark matter, providing the extra gravity needed to account for these speeds. This discovery transformed astronomy. It turned out that the visible universe, all the stars, planets, and gas we can see, represents only about 15% of all matter. The rest, 85%, is dark matter, invisible to all our telescopes. For Andromeda, this meant that even if we could see all its stars, we would still only be measuring a fraction of its total mass. The dark matter halo, extending far beyond the visible stars, was completely undetectable except through its gravitational effects. And measuring those gravitational effects accurately required technology that simply didn't exist until the late 20th century. Chapter 2: The First Signals of Truth. By the late 1990s, something strange was beginning to happen at astronomical observatories around the world. Small anomalies, minor inconsistencies, data that didn't perfectly align with predictions. Individually, each discrepancy could be explained. A measurement error here, a model simplification there, noise in the data over here. But when the most insightful astronomers began to look at the complete picture, a disturbing pattern emerged. Andromeda wasn't behaving as a galaxy with the mass we attributed to it should. The first real hint came from an unexpected place: the dwarf galaxies that orbit Andromeda like cosmic moons around a giant planet. Andromeda has over a dozen of these known satellite galaxies, small structures, some containing barely millions of stars compared to Andromeda's trillion. They orbit at distances of tens or hundreds of thousands of light-years, gravitationally bound to their massive neighbor. Orbital physics is elegantly simple in its essence. The speed at which an object orbits depends directly on the mass of the object it orbits. It's the same physics that governs how the Moon orbits the Earth, or how the Earth orbits the Sun. More mass means more gravity, which means faster orbits to maintain balance. So, when astronomers carefully measured the speeds of Andromeda's satellite galaxies, they expected to find rapid movements consistent with the enormous mass they attributed to Andromeda. But what they found was different. The satellite galaxies were moving slower than predicted. Not dramatically slower, the differences were subtle, but significant enough to make them think. Could it be that Andromeda was less massive than we believed? The idea seemed absurd initially. Decades of observations, hundreds of published studies, countless theoretical models, all converged on the same picture of Andromeda as a giant that eclipsed the Milky Way. Could they all be wrong? Science is conservative, by necessity. We don't discard decades of accumulated knowledge based on a single anomalous observation. So, astronomers did what they always do. They looked for errors in the new data. They checked their calculations. They considered alternative explanations. Perhaps the satellite galaxies had unusually complex orbital histories. Maybe there was invisible mass distributed strangely. Perhaps. The rotation curve clue. But then came more anomalies. Andromeda's rotation curve, a graph showing how rotation speed changes with distance from the galactic center, also didn't fit perfectly. In the 1970s and 80s, astronomers had developed sophisticated techniques to measure these rotation curves using radio telescopes that detected the emission of atomic hydrogen. Hydrogen, the most abundant element in the universe, emits radio waves at a specific wavelength that radio telescopes can detect with precision. By mapping the distribution and speed of hydrogen across Andromeda's disk, astronomers could construct a detailed rotation curve. This curve should correspond directly to the mass distribution in the galaxy. More mass in the center, a steeper curve. Less mass in the outer regions, a flatter curve. But the observed rotation curve of Andromeda was flatter than expected in the outer regions. Again, the discrepancy was subtle, but it was there. And again, it suggested that maybe, just maybe, Andromeda wasn't as massive as we had assumed. The simulation insight. Then there were the computer simulations. As computers became more powerful in the 1990s and early 2000s, astronomers could create increasingly sophisticated models of galactic interactions. They could simulate what would happen when two galaxies collided, tracking the movement of millions of particles representing stars and gas as gravitational forces pushed and pulled them. When astronomers simulated the future collision between Andromeda and the Milky Way using the traditional masses, with Andromeda significantly more massive, the results looked strange. The resulting merged galaxy had properties that didn't align well with what we observe in real elliptical galaxies formed by similar mergers elsewhere in the universe. But when they adjusted the masses to make Andromeda and the Milky Way more similar, the simulations produced results that looked much more realistic. The resulting elliptical galaxy had the structure, velocity distribution, and other properties that matched observed elliptical galaxies. It was as if the universe was dropping hints, whispering that something was wrong with our understanding of Andromeda. But the astronomical community, understandably skeptical of abandoning decades of established knowledge, proceeded cautiously. Hubble's breakthrough in the halo. And then came 2006, the year that marked the true turning point. An international team of astronomers, led by researchers who had been meticulously studying Andromeda's outer regions, published a study that would finally make the astronomical community pay serious attention. They had used the Hubble Space Telescope in an innovative way, focusing not on the bright regions of the galactic center, but on the faint halo that stretches for hundreds of thousands of light years. The galactic halo is a fascinating but frustrating region to study. It contains stars, but they are so scattered that detecting them individually requires extreme sensitivity. These halo stars are generally very old, formed over 10 billion years ago in the earliest epochs of the galaxy's life. They are faint, cold, and hard to see even with the best telescopes. But Hubble could see them. And more importantly, it could measure their motion. Here's the thing. Stars aren't static. They are constantly moving, orbiting the center of their galaxy. From our perspective on Earth, 2.5 million light-years away, these movements are extraordinarily tiny. A star in Andromeda's halo might be moving at hundreds of kilometers per second, but viewed from here, that movement appears as a minuscule displacement in the sky, measurable only in thousandths of an arcsecond. However, Hubble could measure these tiny movements. By photographing the same regions of Andromeda's halo repeatedly over the course of years, astronomers could detect how individual stars changed position over time. It was painstaking, slow, meticulous work, requiring years of dedicated observations and careful analysis. But it was worth it, because the speeds they measured told a clear and unambiguous story. The stars in Andromeda's halo were moving slower than they should if Andromeda had the mass we had attributed to it for decades. It wasn't a minor discrepancy that could be easily explained. It was a significant and systematic difference. The physics was simple and irrefutable. If the halo stars move slower, the galaxy has less mass. There was no avoiding that conclusion. The 2006 study caused a stir in the astronomical community. Skeptics, and there were many, pointed out possible issues. Maybe the measured stars weren't representative of the entire halo. Perhaps there were selection biases in which stars could be measured. Maybe the measurement errors were larger than estimated. But the team had anticipated these criticisms. They had measured hundreds of stars in multiple halo regions. They had carefully analyzed their errors. They had considered every possible bias they could imagine, and their conclusion remained solid. Andromeda was less massive than we thought. Still, a single study, however robust, wasn't enough to overthrow decades of established paradigm. The astronomical community needed independent confirmation. It needed multiple lines of evidence converging on the same conclusion. And that's exactly what happened in the following years. Other teams, using different techniques and different data sets, began to arrive at similar conclusions. Some studied the stellar streams, those long filaments of stars that mark the remnants of satellite galaxies torn apart by Andromeda's tidal forces. The shape and dynamics of these stellar streams depend directly on Andromeda's gravitational field, providing another way to measure its mass. And guess what they found? Less mass than expected. Other astronomers refined the rotation curve measurements using more precise data and improved analysis techniques. Again, they found evidence that Andromeda was less massive than traditionally assumed. Even the most sophisticated computer simulations, run on supercomputers capable of tracking billions of particles, supported the idea that Andromeda and the Milky Way were more similar in mass than we had thought. The evidence was stacking up, converging from multiple independent directions toward the same radical conclusion. But astronomy is a conservative science, and rightly so. Changing an established paradigm requires overwhelming evidence, not just suggestive evidence. That overwhelming evidence would arrive in 2012. A massive team of researchers representing institutions from around the world undertook the most comprehensive study of Andromeda's mass ever conducted. They combined decades of Hubble data with observations from multiple ground-based telescopes. They used every available technique: halo star movements, satellite galaxy dynamics, rotation curves, stellar streams, star formation analysis. They applied the most rigorous statistical methods. They carefully considered all possible sources of error and uncertainty. The analysis took years. The data was massive, complex, and challenging. But when the answer finally emerged, it was clear and unequivocal. Andromeda contains approximately 1 trillion solar masses of matter, roughly the same mass as the Milky Way. The error in previous estimates had been a factor of 2 to 3. For almost a century, we had overestimated Andromeda's mass by 200 to 300%. The 2012 paper was hard to ignore, not only because of the robustness of its methods or the breadth of its data, but because it finally provided the overwhelming evidence the community needed. Multiple independent techniques all converging on the same answer. It could no longer be explained away as a measurement error or selection bias. It was real. Andromeda was not the giant we had believed. It was our cosmic twin. The reaction in the astronomical community was mixed. Some felt vindicated. They had suspected for years that something was wrong with the traditional estimates. Others felt genuine surprise. They had accepted the image of Andromeda the giant without question. And some, frankly, felt embarrassment that such a fundamental error had persisted for so long. But the predominant response, the one that eventually dominated, was fascination, because this discovery completely transformed our understanding of the future collision between Andromeda and the Milky Way. We were no longer talking about an unequal absorption where a giant galaxy devoured a smaller one. We were talking about a merger between true equals. Two cosmic titans of comparable mass uniting in a gravitational dance that would create something completely new. The scientific implications were profound. Models of galactic mergers needed to be revised. Predictions about the resulting galaxy, its shape, size, properties, all changed. Computer simulations needed to be run again with the correct parameters. But there was also a philosophical dimension to this discovery that resonated beyond the astronomical community. For almost a century, we had seen Andromeda as our cosmic superior, a larger and more powerful galaxy that would eventually conquer us. There was something almost humbling about that narrative. We were the little sister destined to be absorbed. But the truth turned out to be much more egalitarian, almost poetic. Andromeda is not our conqueror. It is our twin. And when we finally meet in 4 billion years, it will be like two equal partners uniting, not one dominating the other. However, accepting this new paradigm wasn't instant or universal. Science, to its credit, is skeptical. Even after the 2012 study, some astronomers remained cautious. They wanted to see more confirmation, more data, more independent analysis. And they got it. In the years following 2012, study after study confirmed the new mass measurements. Different teams, using different telescopes and different methodologies, all arrived at the same basic conclusion. Andromeda and the Milky Way are comparable in mass. One of the most elegant confirmation studies came from the analysis of globular clusters, those dense spheres of hundreds of thousands of stars that orbit galaxies like swarms of bees around a hive. Andromeda has over 500 known globular clusters, and each orbits the galaxy following Newton's laws of gravity. By tracking the orbits of these globular clusters, especially those in the outer regions of the halo, astronomers could create an independent map of Andromeda's gravitational field, and this map confirmed the new lower mass estimates. Another approach involves studying the density waves in Andromeda's disk. These waves, the same ones that create the beautiful spiral arms, propagate through the disk in a way that depends on the mass distribution. By carefully analyzing the structure and behavior of these spiral arms, astronomers could infer the total mass of the disk in the central bulge. Again, the results supported the new picture. Andromeda was not the giant we had thought. Perhaps the most convincing was the analysis of dark matter. Recall that the majority of any galaxy's mass is not in the visible stars, but in the invisible dark matter halo surrounding it. This dark matter can only be detected through its gravitational effects. Sophisticated techniques called gravitational lensing, where a galaxy's mass curves the light of more distant objects behind it, allowed astronomers to map the distribution of dark matter around Andromeda. And these maps showed a smaller dark matter halo than previously assumed, consistent with the lower total mass. By 2015, the new paradigm was firmly established. Textbooks began to be updated. University astronomy courses taught the new figures. Scientific conferences discussed the implications. The consensus had shifted. But this paradigm shift raised a fascinating question. If we were so wrong about Andromeda for so long, what else might we be wrong about? The lesson was humbling, but valuable. Even with the best instruments and the brightest minds, our knowledge of the universe is always provisional, always subject to revision as better data becomes available. Science is not a collection of immutable truths, but a continuous process of refinement where each generation builds upon, and sometimes corrects, the work of its predecessors. And there was another aspect to this story worth noting: the importance of technology in scientific advancement. Every major leap in our understanding of Andromeda came from technological improvements. The Hooker telescope allowed us to see further than ever. The Hubble Space Telescope allowed us to observe without atmospheric distortion. Faster computers allowed for more sophisticated simulations. Improved analysis techniques extracted more information from existing data. Without these technological improvements, we would probably still believe Andromeda is a giant. The error would have persisted indefinitely, not because astronomers were incompetent, but simply because they couldn't see what their instruments wouldn't let them see. This leads us to an intriguing reflection on the future. If 20th century technology wasn't enough to correctly measure Andromeda, and it took the Hubble Space Telescope and 21st century technologies to correct the error, what could the technology of the future reveal to us? We are already seeing glimpses of this with the James Webb Space Telescope, launched in 2021. This instrument, with its enormous mirror and ultra-sensitive infrared detectors, is observing Andromeda at wavelengths that Hubble couldn't efficiently access. And it's discovering new details, new stellar populations, new structures that were invisible before. Even more powerful telescopes are in planning or construction. The extremely large telescope, with its 39-meter, approximately 128-foot mirror, will be able to resolve details in Andromeda that are currently impossible to see. Future gravitational wave detectors will be able to study the black holes at the centers of galaxies with unprecedented precision. What will these future technologies reveal about Andromeda? What current assumptions will turn out to be wrong? We can't know, and that's precisely the exciting point. The universe always has more secrets to reveal, always surprises us, always challenges our expectations. The story of the century-long error about Andromeda teaches us scientific humility, but it also teaches us optimism, because if we could correct an error that persisted for almost 100 years, what other cosmic mysteries will we eventually solve? Chapter 3: History's Most Ambitious Mosaic. While astronomers were correcting their monumental error about Andromeda's mass, another extraordinary project was quietly unfolding. It was an undertaking so audacious, so technically challenging that when it was first proposed, some scientists thought it was impossible. The idea was simple to state, but extraordinarily complex to execute: to create the most detailed photograph ever taken of another galaxy. They didn't just want to capture the bright core or the most prominent spiral arms. They wanted to photograph the entirety of Andromeda, edge to edge, with a resolution so high that they could see individual stars across vast stretches of the galaxy. To appreciate the magnitude of this challenge, you need to understand something about how we view Andromeda from Earth. Although it is 2.5 million light-years away, Andromeda is enormous in the night sky. If our eyes were sensitive enough to detect its full, faint extent, it would appear 6 times larger than the full moon. It's a celestial giant, hidden in plain sight, invisible only because most of its light is too dim for our eyes to detect. The Hubble straw problem. The Hubble Space Telescope can certainly see that faint light. The problem is that Hubble, powerful as it is, has a relatively small field of view. It's like looking at the universe through a drinking straw. You can see incredible details in what you're observing, but only a tiny fraction of the sky at a time. To photograph all of Andromeda with Hubble's resolution, astronomers needed to divide the galaxy into thousands of small sections, photograph each one individually, and then assemble all the pieces like a gigantic jigsaw puzzle. Specifically, they needed 7,398 individual exposures. Think about that number for a moment. Nearly 7,500 separate photographs, each one requiring Hubble to point with perfect precision at a specific section of Andromeda, maintain that position with absolute stability while light accumulated in its detectors, and then move to the next section and repeat the process. And this wasn't simply a matter of point and shoot. Each region needed to be photographed in multiple wavelengths of light, different colors that reveal different types of stars and galactic features. Some regions required short exposures. Others needed the telescope to accumulate light for hours to capture the faintest details. The engineering ballet. The planning alone took months. Astronomers created detailed maps of Andromeda, dividing the galaxy into thousands of cells like a cosmic chessboard. They calculated exactly how long Hubble needed to observe each cell. They determined how each image had to slightly overlap its neighbors to ensure there were no gaps in the final coverage. And then the real work began. Years of patient and meticulous observations. Hubble orbits the Earth every 97 minutes, traveling at 17,400 miles per hour, approximately 28,000 kilometers per hour. During each orbit, it spends approximately half the time illuminated by the sun, when it cannot observe faint objects, and half in the shadow of the Earth, when it can observe. This means observation opportunities come in carefully scheduled windows. For each Andromeda exposure, Hubble needed to point with the precision of fractions of an arcsecond, the equivalent of aiming a laser from New York toward a dime in Los Angeles. And it needed to maintain that perfect precision while the telescope orbited, while the Earth rotated beneath, while the entire solar system moved through space. It was a ballet of extraordinary engineering, executed thousands of times over years. Piece by piece, image by image, the mosaic grew. Regions of the dense core where stars are so densely packed they blend into a continuous glow. The spiral arms, where lines of young blue stars trace the density waves. The outer regions of the disk where stars become increasingly scattered and faint. Each new image added more details, revealed more structure, showed more of the beautiful complexity of our neighboring galaxy. Assembling the cosmic jigsaw. But capturing the images was only half the challenge. Once all 7,398 exposures were complete, someone had to assemble them into a coherent mosaic, and that proved to be almost as difficult as taking them in the first place. You couldn't simply paste these images together like an ordinary puzzle. Each exposure was taken at different times, under slightly different conditions. Brightness levels needed to be carefully calibrated to match from one image to the next. Minute optical distortions introduced by Hubble's instruments needed to be corrected. Astronomers developed specialized software for this monumental task. Algorithms that could align images with sub-pixel precision, adjust colors and brightnesses, remove artifacts, building layer upon layer of data until the complete image emerged. Computers worked for months processing terabytes of information. It was a massive computing effort, requiring resources that only a few institutions worldwide could provide. And finally, in 2015, the work was complete. A billion-pixel portrait. The result was spectacular beyond any expectation. The final image contained 1.5 billion pixels. If you printed it at the resolution of a typical photograph, you would need more than 600 high-definition TVs to display it completely. But the numbers barely capture the true magnificence. When you zoom in on different sections of the mosaic, you can see individual stars, not hundreds or thousands, but over 100 million individual stars, each resolvable as a separate point of light. It's like having a stellar census of a massive portion of another galaxy. You can study how different types of stars are distributed across Andromeda. You can identify regions where stars are currently being born. You can trace the populations of ancient stars that formed billions of years ago. You can see structures that had never been visible in such detail before. Dark filaments of dust snaking through the spiral arms, blocking the light of the stars behind them. Bright clusters of young stars, each containing tens of thousands of suns. Massive clouds of hydrogen gas glowing with the energy of newborn stars within them. The Hubble mosaic of Andromeda wasn't just beautiful, though it was certainly breathtakingly so. It was an invaluable scientific tool, a data set that would transform our understanding of how spiral galaxies work. And it immediately began producing discoveries that challenged expectations. Astronomers who studied the distribution of young stars in the spiral arms found unexpected patterns. Instead of being distributed uniformly, as some theoretical models predicted, these stars showed clumping and structures that suggested a more complex and episodic star formation history. There was evidence of multiple star birth waves in Andromeda's past, periods when, for reasons we are still trying to understand, the rate of new star formation dramatically sped up, followed by quieter periods. The mosaic also revealed unprecedented details about interstellar dust. These microscopic particles, made of carbon, silicates, and ices, play a crucial role in star formation by providing the seeds around which gas can condense, initiating the gravitational collapse that eventually gives birth to new stars. Astronomers could track how the dust flows and is distributed across Andromeda, how it is affected by massive star winds, and how it accumulates in the dense molecular clouds where stars are born. They discovered that the dust distribution in Andromeda is remarkably similar to that of our own Milky Way, another confirmation that these two galaxies are truly twins, not only in mass, but also in structure and composition. Perhaps one of the most fascinating findings was about the stellar halo of Andromeda. Beyond the bright disk, extending for hundreds of thousands of light years in all directions, is a diffuse population of ancient stars. These stars are the fossils of galactic formation, witnesses to events that occurred when the universe was young. The Hubble mosaic allowed these halo stars to be studied with unprecedented detail, and what astronomers found was a story of cosmic violence. The halo is not uniform, it is full of substructures, streams of stars, and groupings that reveal their origin. Many of these features are the torn remnants of smaller galaxies. In the distant past, these galaxies ventured too close to Andromeda. The tidal forces, the difference in gravitational pull on different parts of the small galaxy, literally ripped them apart, scattering their stars into long streams that now orbit eternally around their conqueror. It's a sober reminder that galaxies grow by devouring their smaller neighbors. Andromeda has been doing this for billions of years, and it continues to do so today. Several of its current satellite galaxies are gradually being shredded, their stars being stripped away one by one to be incorporated into Andromeda's halo. The mosaic also revealed the complexity of Andromeda's nucleus. Instead of having a single bright center as expected, Andromeda has a double nuclear structure, two distinct concentrations of stars separated by only a few light-years. This strange configuration is probably evidence of a major merger in Andromeda's past. About 2 billion years ago, another sizable galaxy collided and merged with Andromeda. The core of that invading galaxy sank toward the center of Andromeda, but never completely merged with the original nucleus, creating this binary nuclear system that persists to this day. And at the very heart of this complex system lurks a supermassive black hole, a gravitational monster with a mass of 100 to 200 million suns. The Hubble mosaic can't see the black hole directly. No telescope can, because black holes emit no light, but it can see the effects of the black hole on the surrounding stars. By measuring how the stars near the center move, how fast they orbit, astronomers can calculate the mass of the invisible object that must be there to produce those movements. And the answer is unequivocal. There is a massive black hole at the heart of Andromeda, significantly larger than the one inhabiting the center of our Milky Way. The Hubble mosaic of Andromeda represents a landmark in the history of astronomy. It is a testament to what we can achieve when we combine cutting-edge technology with meticulous planning, extraordinary patience, and dedication to scientific exploration. But it is also a reminder that every answer generates new questions. Every detail revealed in the mosaic poses new mysteries. Why has star formation in Andromeda been so episodic? How many small galaxies has it devoured in its history? How exactly did that strange double nuclear structure form? These questions will keep astronomers busy for decades, extracting new science from this extraordinary image. And, in the meantime, they are already planning the next major mapping project. The James Webb Space Telescope, with its infrared capabilities, will create its own mosaic of Andromeda in wavelengths of light that Hubble cannot efficiently access. It will reveal star-forming regions hidden behind dense clouds of dust. It will show populations of cold, ancient stars that are too faint for Hubble. And together, these two extraordinary mosaics, one in visible light, the other in infrared, will give humanity the most complete view of Andromeda ever obtained, revealing our twin galaxy in all its glory across multiple wavelengths of the late electromagnetic spectrum. It's an exciting future for the study of Andromeda, but before looking ahead, we need to fully appreciate what we already know. We need to understand the true dimensions of this extraordinary galaxy that is simultaneously our closest neighbor and our future destination. Chapter 4. Secrets Revealed in the Image. Astronomers who studied the distribution of young stars in the spiral arms of Andromeda found unexpected patterns. Instead of being distributed uniformly, as some theoretical models predicted, these stars showed clumping and structures that suggested a more complex and episodic star formation history. There was evidence of multiple starbirth waves in Andromeda's past, periods when, for reasons we are still trying to understand, the rate of new star formation dramatically sped up, followed by quieter periods, dust, metals, and the inside-out history. The mosaic also revealed unprecedented details about interstellar dust. These microscopic particles, made of carbon, silicates, and ices, play a crucial role in star formation, providing the seeds around which gas can condense, initiating the gravitational collapse that eventually gives birth to new stars. For the first time, astronomers could track how dust flows and is distributed across Andromeda, how it's affected by massive star winds, and how it accumulates in the dense molecular clouds where stars are born. They discovered that the dust distribution in Andromeda is remarkably similar to our own Milky Way. Further confirmation that these two galaxies are truly twins, not only in mass, but also in structure and composition. One of the first important discoveries emerged from studying the chemical composition of the stars. By carefully analyzing the spectrum of light from individual stars in the mosaic, astronomers could determine what they are made of, and what they found was fascinating. A clear chemical gradient from the center to the outer regions of Andromeda. Stars near the nucleus are rich in heavy elements: iron, nickel, carbon, oxygen. These elements were created in the cores of massive stars through nuclear fusion, and then dispersed into space when those stars exploded as supernovae. Stars in the outer regions of the disk, however, are relatively poor in heavy elements. They have compositions more similar to the primordial gas of the early universe, mainly hydrogen and helium, with only traces of heavier elements. This gradient tells a clear story of galactic evolution. Andromeda formed from the inside out. The dense core formed first, over 10 billion years ago. This cycle of star birth, processing, and material return continued for billions of years, making the core chemically rich. Meanwhile, the outer disk grew from gas falling in from the intergalactic medium, which was not enriched as efficiently. The result is the gradient we see today, which is exactly the same pattern seen in our Milky Way. The halo, fossils of cosmic violence. Perhaps one of the most fascinating findings was about Andromeda's stellar halo. Beyond the bright disk stretching for hundreds of thousands of light years is a diffuse population of ancient stars, the fossils of galactic formation, witnesses to events that occurred when the universe was young. The Hubble mosaic allowed these halo stars to be studied in unprecedented detail. What astronomers found was a history of cosmic violence. The halo isn't uniform. It's filled with substructures, stellar streams, and clumps that reveal their origin. Many of these features are the torn remnants of smaller galaxies. In the distant past, these galaxies ventured too close to Andromeda. The tidal forces, the difference in gravitational pull across the smaller galaxy, literally ripped them apart, scattering their stars into long streams that now orbit eternally around their conqueror. This is a sober reminder that galaxies grow by devouring their smaller neighbors. Andromeda has been doing this for billions of years and continues to do so today. The satellites, destruction and renewal. The mosaic also revealed extraordinary details about Andromeda's satellite galaxies. The most prominent is Messier 32, M32, a compact dwarf elliptical galaxy so close to Andromeda that it is clearly being affected by the massive neighbor's tidal forces. The Hubble image showed streams of stars being pulled away from M32, stretched into long filaments by Andromeda's gravity. This is a process of slow-motion destruction. Over the next billion years, M32 will be gradually shredded, its stars eventually dispersed throughout Andromeda's halo. Another notable satellite is Messier 110, M110, or NGC 205. Unlike M32, M110 shows signs of recent star formation, which is unusual for dwarf elliptical galaxies that generally contain only ancient stars. The mosaic revealed regions of young blue stars in M110, suggesting it had an episode of star birth relatively recently. This episode was likely triggered by an interaction with Andromeda itself, where tidal forces compressed M110's gas, triggering a wave of star formation. These satellite galaxies are crucial for understanding how large galaxies grow. According to the hierarchical formation theory, massive galaxies like Andromeda are built gradually through the merging and absorption of smaller galaxies. Andromeda is surrounded by an expected swarm of satellites, some intact, others being shredded, and many already absorbed, leaving only stellar streams, star formation rate, and past mergers. The mosaic also allowed detailed studies of Andromeda's current star formation rate. By identifying regions of young, massive stars, astronomers calculated that Andromeda is currently creating about 1 solar mass of new stars per year. It's a modest rate, similar to our Milky Way, suggesting Andromeda is in a relatively quiet state compared to some intensely star-bursting galaxies. However, the evidence in the mosaic suggests Andromeda experienced multiple, much more intense episodes of star formation in its past, with the distribution of stellar ages showing peaks where many more stars than normal were born simultaneously. These bursts were likely triggered by mergers with other galaxies. When two galaxies collide, their gas clouds smash together violently, and this compression can trigger enormous waves of star birth. Andromeda's last major merger occurred about 2 billion years ago, which likely triggered a massive star formation burst before the galaxy settled into its current quiet state. The core and the monster. The mosaic also revealed the complexity of Andromeda's nucleus. Instead of having a single bright center as expected, Andromeda has a double nuclear structure, 2 distinct concentrations of stars separated by only a few light years. This strange configuration is likely evidence of a major past merger. About 2 billion years ago, another sizable galaxy collided and merged with Andromeda, and the invading galaxy's core sank but never fully merged with the original one, creating this binary nuclear system that persists today. At the very heart of this complex system lurks a supermassive black hole, a gravitational monster with a mass of 100 to 200 million suns. While the Hubble mosaic can't see the black hole directly, no telescope can because black holes emit no light, it can see the black hole's effects on the surrounding stars. By measuring how quickly stars near the center orbit, astronomers can calculate the mass of the invisible object required to produce those movements. The answer is a massive black hole, significantly larger than the one inhabiting the center of our Milky Way. The invisible framework, dark matter. The most profound realization the mosaic reinforces is about dark matter. Recall that the vast majority of any galaxy's mass is not in the stars we can see, but in an invisible halo of dark matter that surrounds the entire visible structure. This mysterious substance doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any way we can directly detect. So, how can we study something that is completely invisible? Through its gravitational effects. Dark matter has mass, and mass produces gravity. By carefully studying how stars and gas move in a galaxy, we can infer the distribution of invisible mass that must be present to produce those movements. The Hubble mosaic, with its precise measurements of the positions and movements of millions of individual stars, provided unprecedented data for mapping the dark matter in Andromeda. The results revealed that Andromeda is encased in a massive dark matter halo that stretches far beyond the visible stellar disk. This halo likely reaches distances of 1 million light-years or more from the galactic center and contains the vast majority of Andromeda's total mass, perhaps 85% or more. It's a humbling reminder of how much of the universe remains invisible to us. When we look at the beautiful mosaic of Andromeda, With its 100 million resolvable stars, we are seeing only the tip of the iceberg. The bulk of the galaxy, the structure that truly holds it together gravitationally, remains completely invisible. Stellar populations and future clues. The mosaic also revealed fascinating patterns in the distribution of different types of stars across Andromeda. Massive, young blue stars, those that shine intensely but live only a few million years, are concentrated in the spiral arms and in regions of active star formation. Mid-aged stars, like our Sun, are more uniformly distributed across the disk. Old, red, and faint stars, those that formed billions of years ago, dominate the central bulge and the halo. This segregation by age and type is not a coincidence. It reflects the galaxy's evolutionary history. One of the most unexpected findings was the discovery of stellar populations that did not easily fit into existing models of galactic evolution. There were groups of stars with ages and chemical compositions that suggested complicated and not fully understood formation histories. Some of these groups are likely the remnants of satellite galaxies that were absorbed in the distant past. Others could represent star formation episodes triggered by mechanisms we still do not fully understand. These anomalies are not problems, they are opportunities. Every feature that does not fit perfectly with our models is a clue the universe is giving us, pointing us toward phenomena we don't yet fully comprehend. The Hubble mosaic of Andromeda will continue to be a source of discovery for decades. Every new analysis, every new technique applied to this data reveals something more. It's a gift that keeps giving, a dataset so rich that it will likely never be fully exhausted. And it represents a model for future studies. But no galaxy will be as important to us as Andromeda. Because Andromeda is not just another galaxy to study, it is our cosmic twin. It is our future. Understanding Andromeda is understanding our own destiny in the universe. Chapter 5. Naked Andromeda. The True Dimensions. Now that we have corrected the century-long error and explored the secrets revealed by the Hubble mosaic, it's time to contemplate Andromeda in all its true magnificence. We need to understand exactly how big this twin galaxy is, what structures compose it, and what makes it so extraordinary. The diameter, a colossal structure. Let's start with the most basic yet most impressive number, the diameter. The visible stellar disk of Andromeda stretches for approximately 220,000 light-years. To put this into human perspective, though acknowledging that cosmic scales defy any human perspective, if you traveled at the speed of light, it would take you 220,000 years to cross Andromeda's disk from one edge to the other. But even this astonishing number tells only part of the story. Beyond the bright disk extends the stellar halo, a diffuse region populated by scattered ancient stars. And this halo is truly colossal. The most distant stars definitively associated with Andromeda have been detected 300,000 light-years from the center, and some estimates suggest that the halo could extend up to 600,000 light-years or more. If we take the complete halo into account, Andromeda is not simply large, it's a structure that spans more than 500,000 light-years of space. It's difficult to comprehend such a scale. Our human mind, evolved to navigate distances of feet and miles, simply has no frame of reference for such vast dimensions. The mass, our cosmic twin. Now let's consider the mass. This is where the correction of the historical error truly matters. Andromeda contains approximately 1 trillion solar masses of matter. 1 trillion. That's 1,000,000,000 stars like our Sun, plus all the accompanying gas, dust, and dark matter. Crucially, this is approximately the same mass as our Milky Way. This equality is not a trivial coincidence. It is fundamental to understanding what will happen when these two galaxies finally collide. The matter breakdown, the invisible majority. But here is a fascinating detail we must understand about that mass. Only a tiny fraction of it is in the form of ordinary matter that we can see. Of that trillion solar masses, perhaps 100 to 200 billion are in stars, gas, and dust, matter that emits or absorbs light in ways we can detect. The rest, the vast majority, is dark matter. This mysterious substance emits no light, absorbs none, and does not interact with electromagnetic radiation in any way we can detect directly. We only know it exists by its gravitational effects. It forms a massive halo around Andromeda, likely extending up to 1 million light-years or more, completely invisible, yet absolutely crucial for holding the galaxy together. It is the gravitational scaffolding upon which all of Andromeda's visible structure was built. Without dark matter, the stars in the outer regions of the disk would move too fast to remain gravitationally bound. They would simply fly off into intergalactic space. The stars and structure, 1 trillion worlds. Now let's talk about the stars. Andromeda contains approximately 1 trillion individual stars. Trying to comprehend this number is almost impossible. If you counted 1 star per second, it would take you more than 30,000 years to complete the census. And these stars come in an astonishing diversity. There are massive blue giants, burning their nuclear fuel so fiercely that they will live only a few million years before exploding as supernovae. There are medium-sized yellow stars like our Sun, shining steadily for billions of years. And there are small, faint red dwarfs that will burn so slowly that some will live for trillions of years, longer than the current age of the entire universe. The distribution of these stars is not uniform. Andromeda has a complex architecture that reflects billions of years of cosmic evolution. The bulge. At the center is the galactic bulge, a dense spherical concentration of primarily ancient stars. This bulge contains tens of billions of stars packed into a relatively small volume. The stellar density there is extraordinary. If you lived on a planet orbiting a star in Andromeda's bulge, the night sky would be spectacular beyond imagination. Millions of stars visible to the naked eye, some so close they would appear as disks rather than points. The disk. Surrounding the bulge is the galactic disk, a flat, rotating structure where the majority of Andromeda's stars reside. This disk is extraordinarily thin considering its vast extent, 220,000 light-years in diameter, but only a few thousand light-years thick. The spiral arms. The disk is structured into spiral arms, those beautiful features that make galaxies like Andromeda so photogenic. But these arms are not solid physical structures. They are density waves, regions where the concentration of stars and gas is slightly greater than in the surrounding areas. As interstellar gas flows through a spiral arm, it is compressed by the increase in density. This compression can trigger the collapse of gas clouds, initiating the formation of new stars. That's why the spiral arms are marked by bright regions of young, hot stars, newly born from the compressed gas and dust. The disk also contains vast amounts of interstellar gas, primarily hydrogen with traces of helium and heavier elements. Andromeda has approximately 10 billion solar masses of gas, enough fuel to sustain star formation for billions of years into the future. The halo. Beyond the visible disk is the halo, that vast spherical region of scattered stars that stretches for hundreds of thousands of light years. The halo contains primarily very ancient stars, poor in heavy elements, formed over 10 billion years ago when the universe was young. It also contains over 500 globular clusters, dense spheres of hundreds of thousands of stars orbiting the galaxy like swarms of bees. The central black hole, the gravitational anchor. And at the very heart of this entire complex system, hidden in the center of the dense stellar bulge, lurks a supermassive black hole. This gravitational monster has a mass of 100 to 200 million suns, compressed into a region of space so small that it is effectively a dimensionless point. This black hole is the gravitational anchor of the entire galaxy. Although it contains only a tiny fraction of Andromeda's total mass, its gravitational influence dominates the central region, controlling the movement of millions of stars in the dense bulge. Currently, the black hole is relatively quiet, consuming material only at a modest rate. But in the past, it likely experienced periods of intense activity when large amounts of gas fell into it, releasing energy that would have made Andromeda's core shine like a beacon, visible across vast cosmic distances. Andromeda's dynamic motion. All this structure, disk, bulge, halo, central black hole, does not exist in a static state. Andromeda is a dynamic system in constant motion and evolution. The entire disk rotates around the galactic center, but not as a solid disk. Different parts rotate at different speeds, a phenomenon called differential rotation. Stars near the center complete their orbits in relatively short times. Stars in the outer regions move slower, taking hundreds of millions of years to complete a single orbit around the galactic center. This differential rotation is crucial for maintaining the spiral arm structure. The density waves propagate through the disk like ripples in a pond, creating those beautiful spiral patterns we see. But the motion is not perfectly circular. Stars also oscillate up and down through the plane of the disk as they orbit, moving inward and outward in complex elliptical orbits. These movements are influenced by irregularities in the gravitational field, the spiral arms, the central bulge, and interactions with nearby satellite galaxies. The halo, in contrast to the ordered disk, does not rotate in an organized manner. Halo stars move in more random orbits, some in one direction, others in the opposite, creating a spherical distribution of movements without the clear structure of the rotating disk. This difference reflects different formation histories. The disk formed from gas that collapsed toward the galaxy's equatorial plane, conserving angular momentum and establishing ordered rotation. The halo formed from material that fell in from all directions, or from shredded satellite galaxies, resulting in more chaotic movements. The inexorable approach. And this entire system is constantly evolving. Stars continue to form from interstellar gas, albeit at a modest rate. Old stars die, returning enriched material to space. Satellite galaxies are gradually absorbed, adding their stars to Andromeda's halo. But perhaps the most dramatic change in Andromeda's future will not come from internal processes. It will come from outside. Because Andromeda is moving through space, drawing inexorably closer to our Milky Way. The two galaxies are currently separated by 2.5 million light-years. It seems like a vast distance, and it is, but on cosmic timescales, it is barely a blink, and that distance is shrinking. Andromeda is approaching us at approximately 110 kilometers per second. That's a tremendous speed by human standards, almost 246,000 miles per hour, approximately 400,000 kilometers per hour. But on cosmic scales, where distances are measured in light years, even this impressive speed translates into a slow, gradual process. At this rate, Andromeda travels approximately 3.5 light-years every million years. It's an inexorable but patient advance across the intergalactic abyss. This movement is driven by the most fundamental force in the universe: gravity. Andromeda and the Milky Way are gravitationally bound. Despite the millions of light years separating them, the mutual gravitational attraction between these two massive galaxies dominates over the general expansion of the universe in our region of space. This attraction has been acting for billions of years, and it will continue to act, gradually accelerating the movement of the two galaxies toward each other, until finally, inevitably, they collide. When will this happen? Based on the most precise measurements available, astronomers predict that the first close encounter between Andromeda and the Milky Way will occur in approximately 4 billion years. 4 billion years. It is an almost incomprehensible amount of time. To contextualize, 4 billion years ago, Earth was a young planet just beginning to develop life. Everything we know about the history of life on our planet has occurred in the last 4 billion years. And in another 4 billion years, two of the largest galaxies in the local universe will begin their merging dance. But understanding Andromeda is not just appreciating its current dimensions or predicting its future. It is recognizing what this galaxy represents to us. It is our most perfect cosmic mirror. It is the only massive spiral galaxy close enough to study in exquisite detail, yet distant enough to see from the outside and appreciate its complete structure. Everything we learn about Andromeda informs our understanding of spiral galaxies in general, and, by extension, our understanding of our own Milky Way. Chapter 6. The Inevitable Destiny, the Collision. 4 billion years in the future, the Earth, if it still exists, will be a radically different world. Our Sun, slowly aging, will have increased its brightness by approximately 40%, causing the oceans to evaporate and the surface to become uninhabitable. But in the night sky, if there were anyone to observe it, the most spectacular show in the history of the local universe would unfold. Andromeda will no longer be a faint smudge visible only on dark nights. It will dominate the sky, a vast, bright structure stretching across much of the celestial vault. And it will be approaching, visibly growing larger with every millennium that passes. But attempting to describe the collision between Andromeda and the Milky Way as a single event is misleading. It will not be a sudden, catastrophic crash. It will be a cosmic dance that unfolds over billions of years, with multiple close encounters before the two galaxies finally merge into a single structure. Let me guide you through how astronomers predict this epic merger will unfold. The first encounter, the tidal dance. The first close encounter will arrive in approximately 4 billion years. At this point, the two galaxies will be close enough that their gravitational fields will begin to interact significantly. The tidal forces, differences in gravitational pull across each galaxy, will start to distort their shapes. Imagine two dancers approaching, their outstretched arms beginning to touch and pull at each other. This is how the dance of Andromeda and the Milky Way will begin. The disks of both galaxies will begin to deform. Stars in the outer regions will feel the gravitational tug of the other galaxy more strongly than the stars near the center. This difference will create tidal forces that will stretch and distort the ordered structures of the disks. Some stars in the outermost regions will be ripped away completely, launched into intergalactic space in long tidal streams. These stellar filaments will stretch for hundreds of thousands of light years, marking the trajectories where the two galaxies approached. But the majority of stars will remain gravitationally bound to their parent galaxies. During this first encounter, the two galaxies will pass right by each other, their shapes distorted but still recognizable as separate structures. The non-collision of stars. And here is something crucial we must understand. Even though we are talking about a collision between galaxies, individual stars will almost never collide with each other. Galaxies are composed primarily of empty space. Stars are separated by distances so vast compared to their sizes that the probability of two stars colliding directly is extraordinarily small. It is as if two swarms of mosquitoes flew through each other. The swarms would mix, but the individual mosquitoes would rarely collide. So, what will happen to our Sun during this first encounter? Almost certainly nothing dramatic. The Sun and its planetary system will pass through the galactic merger without coming dangerously close to any other star. But the Sun's orbit around the galactic center will be significantly perturbed. Currently, the Sun orbits in the disk of the Milky Way, following a relatively ordered path. But during the merger, the tidal forces from Andromeda will launch the Sun into a new orbit, perhaps toward the outer regions of the merged galaxy, or perhaps toward the dense center. We cannot predict with certainty where it will end up. The second encounter, a starburst explosion. After the first encounter, the two galaxies will begin to separate again, but they cannot escape the mutual gravitational pull. Their outward motion will gradually decelerate, stop, and then reverse. The galaxies will begin to approach again for a second encounter. This second encounter, perhaps several 100 million years after the first, will be more dramatic. The two galaxies will be moving faster, pass closer, and the tidal forces will be even more intense. And here is where the interstellar gas plays a crucial role that the stars do not. Unlike the stars which pass by each other without colliding, the gas clouds from the two galaxies will collide directly. When Andromeda's gas impacts the Milky Way's gas at speeds of hundreds of kilometers per second, it will be violently compressed. This compression will trigger a star formation explosion, starburst, unlike any we have seen in billions of years. Where the gas clouds collide, millions of new stars will be born in a relatively short period of cosmic time. These young, massive stars will shine intensely, transforming the collision zones into spectacular stellar nurseries. If there were civilizations observing from safe planets, they would see waves of bright blue light marking the gas impact zones. The final merger, Milkomeda. After the second encounter, the galaxies will separate again, but not as far as before. They have lost energy through tidal forces and gas friction. The third encounter will arrive faster, and so it will continue, encounter after encounter, each one closer than the last, each one losing more energy, until finally, perhaps 6 to 7 billion years from now, the two galaxies can no longer separate. The cores of both galaxies, each containing tens of billions of stars and a supermassive black hole, will sink toward the center of the merged structure. They will orbit around each other in an increasingly tight spiral, losing energy through dynamic friction with the surrounding stars. Eventually, even the two supermassive black holes will meet. They will orbit each other in an ever faster dance, losing energy through the emission of gravitational waves, ripples in the very fabric of space-time. And finally, they will merge. In a fraction of a second, the two black holes, one with 4 million solar masses from our Milky Way, the other with 100 to 200 million solar masses from Andromeda, will combine into a single, even more massive black hole. This merger will release more energy in the form of gravitational waves in that brief instant than all the stars in the observable universe emit as light during the same period. It will be one of the most energetic events possible in the universe, detectable by advanced civilizations billions of light years away. The resulting galaxy, Milkomeda. And when the cosmic dust finally settles, when the last starbursts fade, when the orbits of all the stars stabilize in their new configurations, what will remain will be a galaxy completely different from either of its predecessors. It will no longer be a spiral galaxy with flat disks and elegant arms. The merger will have completely destroyed these ordered structures. Instead, the resulting galaxy will be an elliptical galaxy, a massive spherical distribution of stars without the clear organization of a disk or spiral arms. Astronomers have already given this future galaxy a name, Milkomeda, a combination of Milky Way and Andromeda. It is an appropriate name for the fusion of cosmic twins. Milkomeda will contain all the stars of both original galaxies, approximately 2 trillion stars in total. It will be one of the most massive elliptical galaxies in the local universe, dominating the local group for billions of years to come. The fate of the Sun and Earth. But what will all this mean for life? What will happen to our solar system during this epic galactic transformation? The answer is both comforting and unsettling. As mentioned, the probability of the Sun colliding directly with another star is extraordinarily small. The stars are too far apart. Our solar system will almost certainly pass through the merger without coming dangerously close to any other star. However, the Sun's orbit will be dramatically altered. We currently orbit in the ordered disk of the Milky Way, but during the merger, we will be flung into a new trajectory in the resulting elliptical galaxy. We could end up in the outer regions, far from the dense center. Or we could be thrown toward the central regions, where the density of stars is much higher. But there is another, more important factor to consider. In 4 billion years, when the merger begins, will there still be life on Earth? The answer, almost certainly, is no. But not because of the galactic merger, but because of our own Sun. Stars like the Sun do not shine with constant intensity throughout their lives. As they age, they gradually become brighter and hotter. Stellar models predict that in approximately 1 to 2 billion years, long before the merger with Andromeda begins, the Sun will have heated enough to make Earth uninhabitable. The oceans will evaporate. The atmosphere will be stripped away. The surface will become a desolate, barren desert. And in approximately 5 billion years, the Sun will exhaust the hydrogen in its core and begin its transformation into a red giant. It will expand enormously, perhaps engulfing the orbits of Mercury, Venus, and possibly even the Earth. So, by the time Andromeda and the Milky Way fully merge, the Earth, as a habitable world, will have long since vanished. If humanity or its descendants still exist, they will have had to migrate to other worlds, other stars, perhaps even other galaxies. The cosmic spectacle. But let's imagine for a moment that observers existed on some safe planet orbiting some long-lived star. What would they see during the merger? At first, Andromeda would visibly grow larger in the sky with every millennium that passed. Eventually, it would dominate the night sky, a vast structure stretching across much of the celestial vault. As the two galaxies began to interact, they would see spectacular distortions. The spiral arms of both galaxies would stretch and deform. Long streams of stars would extend into space. During the close encounters, when the gas clouds collided, they would see massive star formation explosions, entire regions of the sky lighting up with the blue light of millions of newborn stars. The night sky would be extraordinarily different from what we see today. Instead of a faint band of the Milky Way, they would see complex structures of light filling much of the sky. And gradually, over millions of years, these structures would merge and reorganize until the new form of Milkomeda finally emerged. It would be the greatest spectacle ever witnessed, a cosmic transformation unfolding over timescales that defy human comprehension, but visible night after night for anyone looking up. And this merger is not unique. It is happening throughout the universe, all the time. Galaxies are constantly merging, combining, and transforming. It is one of the fundamental processes that shapes cosmic evolution. What makes the Andromeda-Milky Way merger special is simply that it is our merger. It is the destiny of our cosmic home. And because of the correction of the century-long error about Andromeda's mass, we now know that it will be a merger between equals, two twins uniting, not a conquest, but a true fusion. Chapter 7: Current Research and the Future of Exploration. While astronomers look toward the distant future of the merger between Andromeda and the Milky Way, they are simultaneously busy studying Andromeda in the present. Every year brings new discoveries, new understandings, and new questions about our twin galaxy. The James Webb Revolution. Infrared light. The James Webb Space Telescope, JWST, launched in December 2021, is transforming our study of Andromeda in ways that Hubble never could. While Hubble observes primarily in visible light, the colors our eyes can see, James Webb is designed to observe in infrared, longer wavelengths of light that are invisible to us, but reveal aspects of the universe that remain hidden in visible light. Why does infrared matter for studying Andromeda? For one critical reason: dust. Interstellar dust, those microscopic particles of carbon and silicates floating between the stars, efficiently blocks visible light. Entire regions of Andromeda, where stars are actively forming, are shrouded in dense dust clouds that are opaque to Hubble. But infrared light penetrates this dust with relative ease. To the James Webb, these obscured regions become transparent, revealing the newborn stars hidden within. Already in its first years of operation, Webb has begun to map star formation regions in Andromeda that were completely invisible to Hubble. It is identifying protostars, stars in the earliest stages of formation, still wrapped in their cocoons of gas and dust. It is tracking how the dust is distributed across the galaxy, how it flows and evolves, and how it participates in the cycle of stellar birth and death. Webb is also studying Andromeda's oldest stellar populations with unprecedented detail. Old, cold stars emit most of their light in the infrared. For Hubble, these stars are faint and difficult to detect. For Webb, they shine brightly. This allows astronomers to map Andromeda's halo, that vast region of ancient stars that stretches for hundreds of thousands of light years, with a precision that was previously impossible. They are discovering new substructure in the halo, new stellar streams marking shredded satellite galaxies, and new evidence of Andromeda's violent history of galactic cannibalism. One of Webb's most ambitious projects is to create a complete census of Andromeda's stellar population, not just counting stars, but determining their ages, chemical compositions, and masses. This will provide an unprecedented understanding of how Andromeda has evolved over cosmic time. When did it experience its largest star formation bursts? How many smaller galaxies has it absorbed in its history? How has its chemical composition changed over time? Webb is working to answer these questions. Earth-based giants and multi-messenger astronomy. But Webb is not working alone. Ground-based telescopes are also contributing crucial observations of Andromeda. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a 39-meter, approximately 128-foot diameter mirror, almost 4 times larger than the largest current ground-based telescopes. When it begins operations in the coming years, it will be able to resolve details in Andromeda that are currently beyond the reach of any telescope. The ELT will be able to study individual stars in Andromeda's distant halo, measuring their movements and chemical compositions with extraordinary precision. It will potentially be able to detect planets orbiting stars in Andromeda, a feat currently impossible for such distant galaxies. And it will be able to study the supermassive black hole at Andromeda's center in unprecedented detail, tracking how gas flows toward it, how it affects the surrounding stars, and how it has evolved over billions of years. Radio telescopes are also making important contributions. The Atacama Large Millimeter Array, ALMA, in Chile is mapping the molecular gas clouds in Andromeda, the dense regions where new stars are born. These observations reveal how gas is distributed across the galaxy, where it is being compressed to form stars, and how star formation is influenced by the large-scale structure of the galaxy. Gravitational wave detectors like LIGO and Virgo, while primarily designed to detect black hole mergers in distant galaxies, are also beginning to contribute to our study of Andromeda. If there are binary black hole systems in Andromeda, two black holes orbiting each other, they will eventually merge and produce detectable gravitational waves. Detecting such events would provide unique information about the black hole population in Andromeda, complementing what we can learn from traditional electromagnetic observations. Simulations and three-dimensional movement. Computer simulations also play an increasingly important role. As supercomputers become more powerful, astronomers can run increasingly detailed simulations of galaxy evolution. Modern simulations can track billions of particles representing stars, gas, and dark matter, modeling how they interact gravitationally over cosmic time. These simulations are helping astronomers understand how galaxies, like Andromeda, formed and evolved, what processes shaped their current structures, and how they will continue to evolve in the future. Simulations of the future merger between Andromeda and the Milky Way have become particularly sophisticated. Astronomers can now predict not only the final result, the elliptical galaxy Milkomeda, but also the details of how the merger will unfold, what will happen during each close encounter, how tidal streams will form, and where star formation bursts will occur. These simulations are constantly being refined as better data is obtained about the masses, structures, and movements of both galaxies. One of the most exciting developments in recent years has been the ability to measure Andromeda's complete three-dimensional movement in space. We not only know that it is approaching us, but we can now also measure its lateral motion across the sky. This was achieved by the European Space Agency's Gaia satellite, which is mapping the positions and movements of over 1 billion stars in our galaxy and beyond. By carefully measuring the positions of bright stars in Andromeda repeatedly over several years, Gaia was able to detect Andromeda's tiny movement across the sky. This lateral movement is crucial for predicting exactly how the future merger will unfold, as the exact angle at which Andromeda hits the Milky Way will significantly affect the merger's details. Gaia's measurements confirmed that the collision is definitely inevitable and refined the predictions about when the first close encounter will occur. The hot gas halo and dark matter theories. Another area of active research is the study of the hot gas surrounding Andromeda. Galaxies do not exist in a vacuum. They are surrounded by enormous halos of extremely hot gas, millions of degrees, that emits X-rays. This gas contains as much mass as all the stars in the galaxy combined, but it is so diffuse that it is difficult to detect. Space-based X-ray telescopes like Chandra and XMM Newton have been mapping this hot gas halo around Andromeda. They are discovering that it extends far beyond the visible stellar disk, potentially reaching distances of several hundreds of thousands of light years. This hot gas plays a crucial role in galactic evolution. It is the reservoir from which colder gas can condense and eventually form new stars. It is also affected by energy released by supernovae and stellar winds, creating a complex cycle of inflows and outflows that regulates star formation. Observations are revealing that Andromeda's gas halo may already be interacting with the Milky Way's gas halo. The two galaxies may be closer than we thought, not in terms of their stars, but in terms of their extended gaseous halos. Astronomers are also using Andromeda as a laboratory to test theories about dark matter. Different theories predict slightly different distributions of this invisible matter. By carefully studying how stars and gas move in Andromeda, astronomers can infer the dark matter distribution and compare it with theoretical predictions. So far, the observations are consistent with the standard model of cold dark matter, particles that move slowly and interact only gravitationally. One of the most intriguing mysteries researchers are currently addressing is why star formation in Andromeda is so modest, despite having so much available gas. With approximately 10 billion solar masses of interstellar gas, Andromeda should, according to some models, be forming stars much faster than we observe. Solving this mystery will inform our understanding of how star formation works in galaxies in general. The horizon of discovery. Looking ahead, there are proposals for even more ambitious observation projects. A concept under discussion is a space interferometer, multiple space telescopes flying in precise formation, combining their light to act as a single giant instrument. Such a system could potentially resolve details in Andromeda that are currently impossible to see with individual telescopes. The study of Andromeda is also benefiting from the growing field of multi-messenger astronomy, the practice of observing the same object using multiple types of signals. Not just light in various wavelengths, but also gravitational waves, neutrinos, and perhaps eventually other cosmic messengers. Together, these signals provide a more complete picture than any could give individually. We are barely beginning to scratch the surface of what Andromeda can teach us. In the coming years and decades, as the James Webb continues its observations, as the extremely large telescope enters operation, and as new space telescopes and gravitational wave detectors are launched, our understanding of Andromeda will deepen dramatically. We will discover more about its history, its current processes, and its future, refining our predictions of how the merger with the Milky Way will unfold. Chapter 8. Final Reflections. Our Place in the Cosmos. There is something deeply moving about contemplating Andromeda. This faint smudge in the night sky, barely visible to the naked eye even on the darkest nights, is actually a colossal structure containing 1 trillion stars, each potentially surrounded by planets, some perhaps harboring life. It is 2.5 million light-years away. The light we see left Andromeda when our human ancestors were just beginning to walk upright on the savannas of Africa. We are literally seeing the distant past, an image of Andromeda as it was millions of years ago, not as it is now at this very instant. And yet, despite this incomprehensible distance, despite the millions of years separating the emission of that light from our observation of it, Andromeda is our closest neighbor among the large galaxies. It is our cosmic twin, and it is our destiny. The lesson of humility and optimism. The story we have explored is extraordinary not only because of its scale, but also because of what it reveals about the nature of human knowledge. For almost 100 years, the global scientific community believed that Andromeda was significantly more massive than our Milky Way. Generations of astronomers operated under this assumption, building models, making predictions, and teaching students, and they were all wrong. But this story is not an indictment of science, it is a celebration of it, because science, at its best, is not a collection of immutable truths, but a process of continuous self-correction. It is the willingness to question long-held assumptions when new evidence emerges. It is the ability to admit monumental errors and then work tirelessly to correct them. The error about Andromeda's mass persisted not because astronomers were lazy or incompetent, but because the tools necessary to correct it simply did not exist. Only when we could place a telescope in space, when we developed detectors sensitive enough to measure individual stellar movements across millions of light-years, when we built computers powerful enough to process massive amounts of data, only then could we finally see the truth. It is a lesson in humility. No matter how certain we are of our current knowledge, we must remember that future generations with better tools will inevitably find flaws in our understanding. Some of our most firmly held beliefs about the universe will turn out to be incorrect. And that is not something to fear. It is something to celebrate, because it means there will always be more to discover, always new mysteries to solve, always new wonders to reveal. The cosmic mirror and our place. The Hubble mosaic of Andromeda represents another kind of human triumph. 7,398 individual exposures, years of patient observations, months of intensive computational processing, all to create a single extraordinary image. Why do this? Because we are a curious species, because we want to understand our place in the cosmos, because the pursuit of knowledge is one of the most fundamentally human endeavors. Andromeda has something to teach us about ourselves. When we look at Andromeda, we are looking at a mirror. It is a spiral galaxy like ours, approximately the same mass, with a similar structure, evolving in a similar way. Everything we learn about Andromeda informs our understanding of our own Milky Way, but it is a mirror we can see from the outside. We cannot see our own galaxy from this perspective. We are trapped inside it. Andromeda allows us to study a twin galaxy from a distance, observe its complete structure, trace its spiral arms, and map its halo. And in doing so, we better understand our own galactic home. Connection and destiny. The future merger between Andromeda and the Milky Way is perhaps the most fascinating aspect of this story. In 4 billion years, these two galaxies will begin their merging dance. Over billions of additional years, they will repeatedly interact, their shapes distorting, their stars intermingling, until they finally merge into a single, giant, elliptical galaxy. This knowledge provides perspective. Andromeda has been approaching for billions of years. It will continue to approach for billions more. It is a process so slow, so gradual, so inevitable, that it puts our human lives into context. And yet, paradoxically, this knowledge also makes human existence seem more precious. We are minuscule beings in a vast cosmos, living for a cosmic blink on a small planet orbiting an ordinary star in a galaxy among billions. But we are beings who can look at the night sky, see that faint smudge called Andromeda, and understand what it is. We are the universe become conscious of itself. We are stellar matter, organized in such a way that it can contemplate the stars from which it came. The study of Andromeda teaches us about the interconnectedness of everything in the universe. Andromeda and the Milky Way were born from the same initial conditions. They evolved similarly, despite being separated by millions of light years. And eventually, they will merge, their stars intermingling, their destinies intertwined forever. The continuing journey. Looking ahead, the James Webb Space Telescope is just beginning its exploration. Every observation reveals new details, new stellar populations, and new structures that were invisible to previous telescopes. The extremely large telescope, when operational, will be able to resolve details currently beyond reach. Future gravitational wave detectors will detect violent events in Andromeda. Every one of these advances will give us new understanding, answer old questions, and, inevitably, pose new ones. Because that is the nature of science. Every answer generates new questions. We are not approaching a point where we will know everything about Andromeda. We are continually discovering how much more there is to learn. The exploration of Andromeda continues. Every clear night, telescopes around the world and in space point toward our twin galaxy, collecting photons that traveled millions of years to reach us, deciphering the secrets encoded in that ancient light. The next time you have the opportunity to see a dark sky, look for that faint little smudge near the Andromeda constellation. When you see it, take a moment to contemplate what you are truly observing. It is not just a point of light, it is a galaxy containing 1 trillion stars. It is our cosmic twin. It is our future destiny. And the light you are seeing left there 2.5 million years ago. It is a moment of connection across the vastness of space and time. Andromeda is more than a scientific object. It is a mirror that shows us who we are, where we came from, and where we are going. It is our past, our present, and our future, all rolled into one faint patch of light in the night sky. If this journey through Andromeda has inspired you, I invite you to subscribe to the Deep Space Calm channel. Every day we explore new mysteries of the cosmos, unravel the secrets of the universe, and celebrate the astonishing power of human curiosity.